Good morning, everyone. Thanks for joining. I want to do a quick video on a topic of a few different things. I had a request come in for an explanation of a few of the different ideas, such as the differences between interfaces and proxy ports, full ports, and differences between ports and pins that you'll see on actions. Also, there's between final flows and activity finals and things of that nature. So thanks for joining. We'll jump right into this. So what you're looking at is a very simple architecture. And in this case, we have what is known as an interface element. So if you look in your containment or in your palette section in Cameo, you'll notice that you have the option for element, and that is available if you are in expert mode. So if you are not in expert mode, you do not have that option. But if you right click for expert mode, you'll see that in a block definition diagram. So really what this interface element is something is mostly used for software interfaces. So if you are a systems engineer and you're defining interfaces, I would recommend typically avoiding using the interface element, because really software engineers use a different term or a different definition for the term interface as systems engineers. So software engineers typically think of an interface as more than simply the line of demarcation between two entities. They actually think of an interface as all of the functionality that is either provided or required by one part of a system in order to communicate across that interface. So what you'll see here is this interface element has the options in the Smart Manipulator and Cameo to actually add properties, or you can add operations, or you can add signal receptions to these. So those really would go into, what is needed functionally for something to communicate across an interface, which is really more than we typically think of as systems engineers when it comes to defining interfaces. And that being said, what systems engineers will use with SysML are proxy ports, full ports, and flow ports. So let's jump into the idea of a proxy port here. So let's say that you have a power generation subsystem. What that proxy port does is simply gives access for some other system to the things that this part of your system can already do, right? And it allows you to either send data across that interface, data that may be something such as the desired power, or even things such as physical phenomenon or energy such as torque, and maybe something such as fuel. So what we are doing really is just giving access to another system to what this system is already doing. That's why this is considered a proxy port in SysML. It's because it doesn't do anything itself, but it gives access to other parts of the system to access those things that this part of your system can do. So that is also slightly different from what we have with full ports. So with full ports, a full port actually can be considered its own part of the system that can have its own features. So it can actually support things such as those operations itself and handle them independently from the part of the system that actually owns that full port. So that is different from a proxy port that cannot actually have any of those types of behaviors. But if you look at a proxy port, or if you type a proxy port with an interface block, which is the only thing a proxy port can be typed as, let's call this the power generation interface. What you'll notice is we can drag this onto the proxy port. We have the ability to add flow properties, reference properties, value properties, operations, receptions, and then nested proxy ports. So what's interesting about this is an interface can actually have references to other things that are blocks as well. So with proxy ports, you actually cannot type a proxy port with a block, right? So let's say that you wanted to call this the power generation interface, and you wanted to try to type that proxy port. SysML does not allow that, and Cameo does not allow that because SysML does not allow that. However, you can type a full port with that block, and then that block could have a lot of other things associated with it, such as constraint properties and a lot of similar things, such as that interface blocks have, minus the other embedded full ports and things of that nature. So what you'll come up against is, okay, well, what's better to use? You know, is it best to use an interface block that types a proxy port, or is it better to use a full port that can be typed by a block? And really, you can essentially get by, I'd say 99.9% of the time, with an interface block and a proxy port. I have seen instances where people will use full ports to differentiate between a physical interface and a logical interface. So that is actually not, it's not based on what SysML intended that to be used for, but I have seen that where you can use that to say all of our logical interfaces use proxy ports with interface blocks, whereas all of our physical interfaces are going to be full ports that are typed by another block. So keep in mind, you can do that to differentiate between the two, but you could also use a stereotype on an interface block that says this is a logical interface or this is a physical interface. And really the difference being, you know, how detailed and specific do you get about what that exact interface is, right? So on the logical side of an interface, you'd want to stay more high level and generic for the most part to say, you know, we're passing things between, you know, or across this interface, such as data, and that could be typed by another block, that can be typed by a block or a signal. And then maybe we have other things such as fuel or things like that. So when it gets into physical interfaces, you're going to be very specific about things such as, well, what type of connector do we use on this interface that we are using to realize that logical interface? So what will actually facilitate the passing of those logical things? And that's what you'll use physical interfaces for. You can also do that with an interface block on a proxy port, and the way you can do that is by using reference properties. So as I mentioned, if you have a full port, you can type that with a block that would define that port. However, if you have an interface block, you can have reference properties. So let's say this reference property is called a 21-pin connector, for instance. That 21-pin connector can be a block that is called a 21-pin connector, right? So let's use some other block here. So let's do 21-pin connector, right? Whoop, I meant to type that one there. Okay, we'll delete this one here. So that is a way that you can also describe the physical solution to this interface by using reference properties. This could be typed as a physical connector or something of that nature, and then this can have mass as well. I've seen some videos out there that Mike Vanarchik has done on this topic, where he'll describe using a block that you can use to actually add those properties to, such as the mass of this. And, you know, that is great to do because that would actually be a physical part of your system that you'd want to have rolled up into your complete mass roll-up and things like that. So a lot of different approaches here, but I digress slightly. And really my main point in all of this is to say, if you're a systems engineer, I would typically avoid using the interface element, as that is more of a software term. But if you're a systems engineer, I would recommend that you stick with mostly trying to use interface blocks on proxy ports. And as I said, you can always use additional stereotypes to differentiate between logical interfaces or physical interfaces, or you could assign that logical stereotype even to the different flow properties that you have in that interface block as well, whereas this one might be typed as a physical property of that interface block. So a lot of different approaches to this. There's not necessarily a right or wrong way, but there are a lot of ways where you can help yourself out and help other people to understand really what you're trying to convey, which is the main point. So the next topic I want to jump into is ports versus pins. So if you're dealing with your structural architecture such as this, a proxy port is considered a port, full port is considered a port. Of course, there are a few other types of ports as well, such as the flow ports and the standard port, which is going to be deprecated. But what's the difference between that and a pin? Well, a pin is something that you'll see on an action. So let's go into a behavioral diagram. Let's see here. So if we jump into this behavioral diagram, this is an activity diagram. What you'll notice is these are pins, right? And really this is what is used to convey the movement of objects between different functions or different actions that can be typed by other behaviors. So in this case, notice we have a call behavior action, and what we're doing is we're telling it that it has a parameter that is called desired power that's typed by a watt. And in this case, what that means is this activity that's called manage fuel flow has an input parameter. So if we look up here at the containment tree, we see manage fuel flow, and then it has a list of parameters next to it. So the parameters that this behavior has are desired power typed by watt, and also desired fuel flow, which is the output of that. I'm sorry, that's the desired fuel flow. Let's see. It looks like these are not synced up, which is also going to be an issue. So let's say we go ahead and we validate this. I believe we will see an error here because this is called desired power, whereas it looks like the parameters are desired power and desired fuel flow. So it's not throwing an error at us currently, but let's say we actually drag this out onto the diagram. It should create another call behavior action with those pins, and really that's what it should say, right? It should have desired power here and desired fuel flow coming out, because that's what would match the activity that types that action. So in this case, we could literally delete that action and bring this in here. That way it actually is matching up. I'm not sure why the validation did not actually check for that. It should have, and then in that case, what you can do is sync up your actions with your behaviors, because this is simply a call behavior action that can call the behavior of this activity. So getting back to the idea of pins versus ports, pins are really the usage of an activity parameter. So if we were to delve into this with another activity diagram that elaborates upon this, what you'll see is that pin is then going to be an activity parameter at that lower level. So let's do that. So let's create a diagram. We'll create another lower level activity diagram that delves into that. And let's say, okay. And notice it's asking you, well, which one of these parameters would we like to display in this diagram? And those actually become activity parameter nodes at this lower level. So at the higher level, at the action, the usage level, that was a parameter of the activity. And on that action, it was a pin. But now when we delve one level deeper, this is actually now considered an activity parameter node. So what would happen is, let's say we have desired power and desired fuel flow rate here. You could add some other function here that transforms the desired power in watts to that desired fuel flow rate. And then you could actually simulate that as well and have something else for the fuel flow rate pop out of this at that higher level. And then, of course, it would actually pop out of this pin up here. So you're just looking at that at different levels of abstraction, essentially, at that point. So that's really the differences between ports, pins, activity parameters. One question that comes up in a lot of projects is when to use accept event actions, or when should we use things such as activity parameter nodes and pins. So really a good rule of thumb for this is if you are attempting to convey that there is some discrete event that happened, even if that discrete event, such as a software message, has some data associated with it, such as desired power, I would typically use an accept event action, because that is really an asynchronous event that, you know, we're receiving that and then we're moving on and doing other things. Whereas you can have an activity parameter even at this high level. And if this were a use case, you can use this context frame to convey that this is coming in from outside of that part of your system that actually executes this activity. So let's say that the power subsystem is executing this generate power. Well, by placing this activity parameter on the edge of this diagram, that actually means that there will be something coming in from outside of this part of the system that will then be used in this activity. Notice, however, that the accept event could also be coming in from outside of that boundary. So you're still left with the question of, well, should I use an accept event action to show that that's coming in from outside of the boundary of the system? Or should I use an activity parameter node? And theoretically, that could convey the same thing, right? Right. However, if you get into things such as, let's say we wanted to type this by some certain amount of power, right? Like, let's say we had a low voltage power coming in. So let's create another block for our low voltage power. We'll call it low voltage DC power, and then we can type this here. What you can also get into is the idea of streaming versus continuous. So let's say we send this to one of these activities that makes no sense, but we can then assign continuous to this, and we can assign that to this object flow as well. So let's say that's continuous. This could also be a stream, meaning that it continues to accept more tokens as this activity is executing. So by stream, we can then add a rate to this and say that there is some certain rate at which we are receiving things. And that's different from what we would see with this accept event action. So the accept event action is really that discrete event that we receive something here. It provides that data, if there's data, matter, or energy out of that pin that pops out of that. And I think that's a great rule of thumb to use if you're trying to determine whether or not you should be using accept event actions or if you should be using activity parameter nodes. But keep in mind, at a higher level, this activity parameter is actually a pin of this activity. So that's really one and the same. And I think you can use that rule of thumb as a good guide to know whether or not you should be using accept event actions, or at the use case level, whether you should be using simply an activity parameter node. And as I mentioned, if you have a specific part of your system, this does convey that that comes from outside of that part of the system that executes this. However, these accept event actions can also come from outside the system. So one little tip for that is if you're using specific naming conventions, you can give an indication that this is coming from outside the system by adding a specific word such as transmitted. And if it's something that's coming from within that system, it could say sent rather than transmitted. So there are some different little tricks you can use. You can also use a stereotype. And that's actually one thing I would recommend is stereotyping accept event actions such as, which port it would enter through, right? So you can actually add that to this as well, and then define a port, and then that can help to inform your ICDs as well. So great topics there to discuss. Hopefully that makes sense. One other quick thing I want to add to the end of this is the idea of activity final versus a flow final. So this is one of those little SysML things, but really the idea is that if we were to simulate this, an activity final is going to stop this behavior completely, whereas a flow final is not going to end the behavior, it's only going to stop that flow. And that's typically, flow finals are typically what we would use if you have concurrent flows. So if we have two concurrent flows where you may have forked something out, notice we got to the activity final and it stopped. Let's say we had some fork that was here, and then maybe we'll add some wait event here for no reason, and then we'll say that we wait 60 seconds there, and we'll make that relative by changing its property here, and that'll say after 60 seconds. So then we have this fork here, but let's send that also out to the activity final. What's essentially going to happen is this is just going to stop right here. But as I mentioned, that's really typically what you would use if you're indicating that you want to kill a flow when you may have other flows happening at the same time. So let's run this momentarily and you'll see what happens to that token as it gets down there. So let's send the desired power signal. We'll notice when this gets down here, this will wait, but then this token here that hits the flow final should just simply stop. And that ends right there. And that's a good way to kill a flow if you'd like to. So hopefully this has been helpful. If you have any questions on this, please feel free to reach out. Thank you very much.